Welcome back to the deep dive. Today we're digging into something for anyone who uses Python and, wants to move past just writing code that works.
Right, from it runs to it runs beautifully.
Exactly. We're talking about writing code that is undeniably efficient and, well, elegant. We're diving into Python's built-in data structures and that often underestimated collections module.
hmm The source material we looked at gives us a great blueprint for these specialized tools. They're containers that aren't just for holding data.
Okay, so what are they for?
They're designed to handle really specific organizational problems. Things like counting frequencies, making sure things stay in order, or managing queues. And the key is they do it with way better performance.
Better than your standard lists and dictionaries.
Oh, much better. Our mission today is to really distill what these things do and show you exactly when you should stop reaching for a generic list and, start using one of these specialists.
So if you're looking for those little aha moments that can really change how you code, this is for you.
Definitely. And we'll start with some quick foundational helpers. The first one is the zip function.
Okay, zip. Let's unpack that. It's all about efficiency, isn't it? It just takes a bunch of lists or other iterables and sort of mashes them together.
It merges them, yeah, pairing up elements one by one into a list of tuples.
And that list of tuples is the perfect stepping stone for what? Building dictionary?
Exactly. Building them fast. The source material had a couple of really good examples of where zip just shines.
Right, the first one was mapping every lowercase letter to its position in the alphabet. So A goes to 1, Z to 26.
You could do that with a loop, but it's kind of clunky.
Yeah, but with zip, you just take a string of the alphabet, a range of numbers, and zip them. It's one clean line.
And that idea scales up. You could map those letters to their ASCII values instead, like A to 97. You just zip the alphabet string with the numbers. It's clean, it's readable, and it's fast.
Okay, so we've used zip to create things efficiently. Now let's talk about structures that organize data, like the set types.
So a set object is, by definition, an unordered collection of distinct hashable objects.
The key word there is distinct, right?
Distinct is everything. You use a set when you only care if something exists in the collection. You don't care about duplicates, you don't care about the order.
And this is where that performance complexity thing comes in, which is so important. If I look for an item in a huge list, I might have to check every single element. That's ON.
Correct. It can be slow. But because sets use hashing, checking for membership is, on average, O1. Constant time. It's incredibly fast.
And that's the difference between your code taking seconds versus maybe hours on a big enough data set.
It really is. That's not an exaggeration.
So what's the deal with set versus a frozen set?
It's all about mutability. A standard set is mutable. You can add things, remove things. A frozen set is immutable. Once you make it, you can't change it.
And why does that matter?
Because only immutable things can be hashable. So you can put a frozen set inside another set, or you can use it as a key in a dictionary. You can't do that with a regular set.
I see. It opens up more complex ways to structure your data.
Exactly. Calculating things like set differences becomes a core part of solving certain problems.
Okay, that feels like a good transition. Let's get into the collections module itself. These are like superpowered dictionaries, right?
They're subclasses of dict, yeah, with unique, highly optimized behaviors. And the first one you should know is counter,
For counting things, I assume.
specifically for counting hashable objects. If you need a quick word histogram from a text file or you're tallying votes, counter is your tool. It's made for that.
What's interesting is how it handles ties. The source mentioned that if two items have the same count, counter remembers which one you saw first.
It remembers the insertion order of the key. That can be really important for tie-breaking logic.
So for something like that Zipf's law problem, you'd use a counter.
You would. But you'd also have to remember all the little details, like parsing character by character, ignoring the case, throwing out tiny words.
Right. Now let's talk about a mistake every single person makes with dictionaries. The key error. You try to get a key that isn't there, and boom, program crashes.
Yes. And that's where defaultdict is just a game changer.
Tell me about it.
It's a simple idea, but it's brilliant. Instead of throwing an error for a missing key, it calls a factory function that you give it.
Like default list.
Exactly. If you use default list, anytime you try to access a new key, it just creates an empty list for you right there. You can just start appending to it immediately.
That gets rid of all that ugly boilerplate code, the whole if key and dict check. I remember writing so much of that.
We all do. But the real power comes when you combine these things. Let's say you're mapping students to their courses.
Okay.
You could use a cattle counter to track how many students are in each course, but then use a default GIC set to map the course name to a set of unique student IDs.
Ah, so you get the super fast lookups from the set with the automatic creation from the defaultdict. That's clever.
It is. Now let's talk about order. Let's talk about orderdict.
This is a big one. It's a dictionary that, well, remembers the order you added things. But here's the question I always have. Modern Python dictionaries, since like 3.7, also remember insertion order. So why do we still need orderdict?
That's a fantastic question. It gets right to the heart of it. While standard dicts do keep order now, orderdict gives you very specific, guaranteed behaviors that are crucial for certain things.
Like what? What's the key difference?
The crucial detail is what happens when you override a key. In an orderdict, if you change the value of an existing key, that key gets moved to the end of the order.
Oh, I see. A standard dictionary wouldn't do that. It would just update the value in place.
Correct. And that automatic move to end behavior is absolutely essential for things like MRU and LRU caches.
Most recently used and least recently used.
Exactly. In an LRU cache, the whole point is that when you access an item, it should become the most recently used. Orderdict does that for you automatically. The item at the front is always the oldest, ready to be kicked out.
And it has special methods for this too.
It does. It has a method to pop a pair off, and you can tell it whether to take from the end LIFO, last in, first out, or from the beginning, FIFO. It gives you precise control over that history.
Okay, that makes perfect sense. And it leads us right into structures that are purely about managing data flow, stacks and queues. Let's talk about dict.
The dig pronounced deck is a wonderful list-like container. Its whole deal is super fast, appends and pops from either end.
And we need to hit the performance angle again. With a normal Python list, adding or removing from the beginning is really slow if the list is big.
It's terrible. It's ON. Because every single other element has to be shifted in memory. It just kills performance.
But a deck.
A deck does it in constant time, O1 at either end, head or tail. That two-sided speed is what makes it perfect for simulating queues, where you're adding to one end and removing from the other.
So for something like that overnight oats problem from the source, a simulation of a sequence of deck would be the obvious choice.
The perfect choice. But what if the order isn't about when something arrived, but about its priority?
Then you need something else.
Then you need heapq. That's Python's module for min-max priority queues.
Okay, for someone who hasn't used heaps before, what's the core idea?
Think of it like a binary tree that's always partially sorted. In Python's version, it's a list where any parent node is always smaller than or equal to its children.
Which means the smallest item is always right at the top, at the root.
Always. Which makes it a min priority queue by default. You can always get the smallest item instantly.
That's great if you want the lowest cost task, but what if I need a max priority queue? What if I want the biggest item?
Simple trick. You don't need a new data structure. You just negate the values when you push them onto the heap.
Oh, so the biggest positive number becomes the smallest, most negative number.
Exactly. It rises to the top. Then when you pop it off, you just negate it again to get the original value back. It's a clever, simple solution.
And how do you build one?
Two main ways. You can just start with an empty list and use heap push to add elements one by one. Or if you already have a list of stuff, you can use heapify to turn it into a valid heap in place, which is usually faster.
This kind of constant reordering seems vital for things like dynamic task scheduling or complex simulations.
It is. Which brings us to our last big point. We need to connect all of these tools back to that trade-off. Performance versus convenience.
Right. It's one thing to know the tool exists. It's another to know when the generic option is actually a performance trap.
Let's look at the CD problem. The task is to find common items between two huge lists. The obvious first thought is set intersection.
It screams set intersection.
But the source gave a huge warning here. It said, for this specific context, do not use the built-in set intersection. It's actually slower in Python for these massive data sets.
Slower.
Yeah.
But sets are a 1 for lookups. How can it be slower?
It's the overhead. The cost of creating the sets, hashing all those millions of items, it adds up. It turns out that for this problem, just sorting both lists and then walking through them together is faster.
That is a fascinating detail. It shows that theory isn't everything. Implementation matters.
It's a huge lesson. Now, that's not to say sets are bad. In most cases, they're the right tool. If you're tracking which users are cheaters and which are hunters in a game, you'd absolutely use two sets.
And we also saw examples of mixing and matching, right? Like using a stack, which you'd build with a deck right alongside a set for parsing something.
Right. So the big takeaway is that these structures, counter, dict, heap, default, dict, They're optimized blueprints. They handle the hard work of managing order, duplication, and priority for you, usually in a one time.
They save you development time and they save you computational energy.
And understanding them is the key to writing fast, clean, modern Python code. It's about knowing how a structure handles change.
Okay, so let's leave our listener with one final thought, something to chew on.
Let's do it. This raises a really important design question. Imagine you're building a feature that relies heavily on data history, a complex underrated feature, for example.
Okay, a practical application.
How does that specific guaranteed behavior of the order dict, where overwriting a key moves it to the end, force you to think differently compared to just using a deck? A deck just handles adding and deleting from the ends.
Right. The order dict is tracking a history of access and mutation, while the deck is only tracking the sequence of additions and deletions.
Exactly. So which design choice buys you more efficiency and, more importantly, more clarity when you're trying to track an object's lifecycle, and why?
That's a great question. The answer is in the details of the methods each one provides.
It is. And digging into that is why we move beyond the basics.
That's all the time we have for this deep dive. Go explore the Python docs and put these specialized tools to work.